Tantor Audio, a division of Recorded Books, presents The Laws of Thermodynamics, a very short introduction, by Peter Atkins, narrated by Nick Sullivan.
Preface. Among the hundreds of laws that describe the universe, there lurks a mighty handful. These are the laws of thermodynamics, which summarize the properties of energy and its transformation from one form to another. I hesitated to include the word thermodynamics in the original title of this little introduction to this boundlessly important and fascinating aspect of nature, hoping that you would listen at least this far, for the word does not suggest a light listen. And indeed, I cannot pretend that it will be a light listen. When in due course, however, you emerge from the other end of this slim volume with your brain more sinewy and exercised, you will have a profound understanding of the role of energy in the world. In short, you will know what drives the universe. Do not think that thermodynamics is only about steam engines. It is about almost everything. The concepts did indeed emerge during the 19th century when steam was the hot topic of the day, but as the laws of thermodynamics became formulated and their ramifications explored, it became clear that the subject could touch an enormously wide range of phenomena, from the efficiency of heat engines, heat pumps, and refrigerators, taking in chemistry on the way, and reaching as far as the processes of life. We shall travel across that range in the pages that follow. The mighty handful consists of 4 laws, with the numbering starting inconveniently at 0 and ending at 3. The first 2 laws, the Zeroth and the first, introduce 2 familiar but nevertheless enigmatic properties, the temperature and the energy. The third of the 4, the second law, introduces what many take to be an even more elusive property, the entropy, but which I hope to show is easier to comprehend than the seemingly more familiar properties of temperature and energy. The second law is one of the all-time great laws of science, for it illuminates why anything from the cooling of hot matter to the formulation of a thought, happens at all. The fourth of the laws, the third law, has a more technical role, but rounds out the structure of the subject, and both enables and foils its applications. Although the third law establishes a barrier that prevents us from reaching the absolute zero of temperature, of becoming absolutely cold, we shall see that there is a bizarre and attainable mirror world that lies below zero. Thermodynamics grew from observations on bulk matter, as bulky as steam engines in some cases, and became established before many scientists were confident that atoms were more than mere accounting devices. The subject is immeasurably enriched, however, if the observation-based formulation of thermodynamics is interpreted in terms of atoms and molecules. In this account, we consider first the observational aspects of each law, then dive below the surface of bulk matter and discover the illumination that comes from the interpretation of the laws in terms of concepts that inhabit the underworld of atoms. In conclusion, and before you roll up the sleeves of your mind and get on with the business of understanding the workings of the universe, I must thank Sir John Rowlandson for commenting in detail on 2 drafts of the manuscript. His scholarly advice was enormously helpful. If errors remain, they will no doubt be traced to where I disagreed with him. Chapter 1. The Zeroth Law. The Concept of Temperature. The Zeroth Law is an afterthought. Although it had long been known that such a law was essential to the logical structure of thermodynamics, it was not dignified with a name and number until early in the 20th century. By then, the first and second laws had become so firmly established that there was no hope of going back and renumbering them. As will become apparent, each law provides an experimental foundation for the introduction of a thermodynamic property. The Zeroth law establishes the meaning of what is perhaps the most familiar but is in fact the most enigmatic of these properties, temperature. Thermodynamics, like much of the rest of science, takes terms with an everyday meaning and sharpens them, some would say hijacks them, so that they take on an exact and unambiguous meaning. We shall see that happening throughout this introduction to thermodynamics. It starts as soon as we enter its doors. The part of the universe that is at the center of attention in thermodynamics is called the system. A system may be a block of iron, a beaker of water, an engine, a human body. It may even be a circumscribed part of each of those entities. The rest of the universe is called the surroundings. The surroundings are where we stand to make observations on the system and infer its properties. Quite often, the actual surroundings consist of a water bath maintained at constant temperature, but that is a more controllable approximation to the true surroundings, the rest of the world. The system and its surroundings jointly make up the universe. Whereas for us the universe is everything, for a less profligate thermodynamicist it might consist of a beaker of water, the system, immersed in a water bath, the surroundings. A system is defined by its boundary. If matter can be added to or removed from the system, then it is said to be open. A bucket, or more refinedly an open flask, is an example because we can just shovel in material. A system with a boundary that is impervious to matter is called closed. A sealed bottle is a closed system. A system with a boundary that is impervious to everything in the sense that the system remains unchanged, regardless of anything that happens in the surroundings, is called isolated. A stoppered vacuum flask of hot coffee is a good approximation to an isolated system. The properties of a system depend on the prevailing conditions. For instance, the pressure of a gas depends on the volume it occupies, and we can observe the effect of changing that volume if the system has flexible walls. Flexible walls is best thought of as meaning that the boundary of the system is rigid everywhere except for a patch, a piston, that can move in and out. Think of a bicycle pump with your finger sealing the orifice. Properties are divided into two classes. An extensive property depends on the quantity of matter in the system, its extent. The mass of a system is an extensive property. So is its volume. Thus, 2 kilograms of iron occupies twice the volume of 1 kilogram of iron. An intensive property is independent of the amount of matter present. The temperature, whatever that is, and the density are examples. The temperature of water, drawn from a thoroughly stirred hot tank, is the same regardless of the size of the sample. The density of iron is 8.9 grams per cubic centimeter, regardless of whether we have a 1 kilogram block or a 2 kilogram block. We shall meet many examples of both kinds of property as we unfold thermodynamics, and it is helpful to keep the distinction in mind. Introducing equilibrium. So much for these slightly dusty definitions. Now we shall use a piston, a movable patch in the boundary of a system, to introduce one important concept that will then be the basis for introducing the enigma of temperature and the Zeroth law itself. Suppose we have two closed systems, each with a piston on one side and pinned into place to make a rigid container. The two pistons are connected with a rigid rod so that as one moves out, the other moves in. We release the pins on the piston. If the piston on the left drives the piston on the right into that system, we can infer that the pressure on the left was higher than that on the right, even though we have not made a direct measure of the two pressures. If the piston on the right won the battle, then we would infer that the pressure on the right was higher than that on the left. If nothing had happened when we released the pins, we would infer that the pressures of the two systems were the same, whatever they might be. The technical expression for the condition arising from the equality of pressures is mechanical equilibrium. Thermodynamicists get very excited, or at least very interested, when nothing happens, and this condition of equilibrium will grow in importance as we go through the laws. We need one more aspect of mechanical equilibrium. It will seem trivial at this point, but establishes the analogy that will enable us to introduce the concept of temperature. Suppose the two systems, which we shall call A and B, are in mechanical equilibrium when they are brought together and the pins are released. That is, they have the same pressure. Now, suppose we break the link between them and establish a link between system A and a third system C equipped with a piston. Suppose we observe no change. We infer that the systems A and C are in mechanical equilibrium, and we can go on to say that they have the same pressure. Now, suppose we break that link and put system C in mechanical contact with system B. Even without doing the experiment, we know what will happen: nothing. Because systems A and B have the same pressure, and A and C have the same pressure, we can be confident that systems C and B have the same pressure, and that pressure is a universal indicator of mechanical equilibrium. Now we move from mechanics to thermodynamics and the world of the Zeroth law. Suppose that system A has rigid walls made of metal, and system B likewise. When we put the two systems in contact, they might undergo some kind of physical change. For instance, their pressures might change, or we could see a change in color through a peephole. In everyday language, we would say that heat has flowed from one system to the other, and their properties have changed accordingly. Don't imagine, though, that we know what heat is yet. That mystery is an aspect of the first law, and we aren't even at the Zeroth law yet. It may be the case that no change occurs when the two systems are in contact, even though they are made of metal. In that case, we say that the two systems are in thermal equilibrium. Now, consider three systems, just as we did when talking about mechanical equilibrium. It is found that if A is put in contact with B and found to be in thermal equilibrium, and B is put in contact with C and found to be in thermal equilibrium, then when C is put in contact with A, it is always found that the two are in thermal equilibrium. This rather trite observation is the essential content of the Zeroth law of thermodynamics. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then C will be in thermal equilibrium with A. The Zeroth law implies that just as the pressure is a physical property that enables us to anticipate when systems will be in mechanical equilibrium when brought together, regardless of their composition and size, then there exists a property that enables us to anticipate when two systems will be in thermal equilibrium, regardless of their composition and size. We call this universal property the temperature. We can now summarize the statement about the mutual thermal equilibrium of the three systems simply by saying that they all have the same temperature. We are not yet claiming that we know what temperature is. All we are doing is recognizing that the Zeroth law implies the existence of a criterion of thermal equilibrium. If the temperatures of two systems are the same, then they will be in thermal equilibrium when put in contact through conducting walls, and an observer of the two systems will have the excitement of noting that nothing changes. We can now introduce two more contributions to the vocabulary of thermodynamics. Rigid walls that permit changes of state when closed systems are brought into contact, that is, in the language of Chapter 2, permit the conduction of heat, are called diathermic, from the Greek words for through and warm. Typically, diathermic walls are made of metal, but any conducting material would do. Saucepans are diathermic vessels. If no change occurs, then either the temperatures are the same, or, if we know that they are different, then the walls are classified as adiabatic, impassable, we can anticipate that walls are adiabatic if they are thermally insulated, such as in a vacuum flask, or if the system is embedded in foamed polystyrene. The Zeroth law is the basis of the existence of a thermometer, a device for measuring temperature. A thermometer is just a special case of the system B that we talked about earlier. It is a system with a property that might change when put in contact with a system with diathermic walls. A typical thermometer makes use of the thermal expansion of mercury or the change in the electrical properties of material. Thus, if we have a system B, the thermometer, and put it in thermal contact with A, and find that the thermometer does not change, and then we put the thermometer in contact with C and find that it still doesn't change, then we can report that A and C are at the same temperature. There are several scales of temperature, and how they are established is fundamentally the domain of the second law, see Chapter 3. However, it would be too cumbersome to avoid referring to these scales until then, though formally that could be done, and everyone is aware of the Celsius, centigrade, and Fahrenheit scales. The Swedish astronomer Anders Celsius, 1701 to 1744, after whom the former is named, devised a scale on which water froze at 100 degrees and boiled at 0 degrees, the opposite of the current version of his scale, 0 degrees Celsius and 100 degrees Celsius, respectively. The German instrument maker Daniel Fahrenheit, 1686 to 1736, was the first to use mercury in a thermometer. He set 0 degrees at the lowest temperature he could reach with a mixture of salt, ice, and water, and for 100 degrees he chose his body temperature, a readily transportable but unreliable standard. On this scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. The temporary advantage of Fahrenheit's scale was that with the primitive technology of the time, negative values were rarely needed. As we shall see, however, there is an absolute zero of temperature, a zero that cannot be passed, and where negative temperatures have no meaning except in a certain formal sense, not one that depends on the technology of the time. See Chapter 5. It is therefore natural to measure temperatures by setting 0 at this lowest attainable zero, and to refer to such absolute temperatures as the thermodynamic temperature. Thermodynamic temperatures are denoted T, and whenever that symbol is used in this book, it means the absolute temperature with T equals 0 corresponding to the lowest possible temperature. The most common scale of thermodynamic temperatures is the Kelvin scale, which uses degrees, kelvins, K, of the same size as the Celsius scale. On this scale, water freezes at 273 kelvins. That is, at 273 Celsius-sized degrees above absolute zero. The degree sign is not used on the Kelvin scale, and boils at 373 kelvins. Put another way, the absolute zero of temperature lies at negative 273 degrees Celsius. Very occasionally, you will come across the Rankine scale, in which absolute temperatures are expressed using degrees of the same size as Fahrenheit's. The molecular world. In each of the first 3 chapters, I shall introduce a property from the point of view of an external observer. Then I shall enrich our understanding by showing how that property is illuminated by thinking about what is going on inside the system. Speaking about the inside of a system, its structure in terms of atoms and molecules is alien to classical thermodynamics, but it adds deep insight, and science is all about insight. Classical thermodynamics is the part of thermodynamics that emerged during the 19th century, before everyone was fully convinced about the reality of atoms and concerns relationships between bulk properties. You can do classical thermodynamics even if you don't believe in atoms. towards the end of the 19th century, when most scientists accepted that atoms were real and not just an accounting device, there emerged the version of thermodynamics called statistical thermodynamics, which sought to account for the bulk properties of matter in terms of its constituent atoms. The statistical part of the name comes from the fact that in the discussion of bulk properties we don't need to think about the behavior of individual atoms, but we do need to think about the average behavior of myriad atoms. For instance, the pressure exerted by a gas arises from the impact of its molecules on the walls of the container. But to understand and calculate that pressure, we don't need to calculate the contribution of every single molecule. We can just look at the average of the storm of molecules on the walls. In short, whereas dynamics deals with the behavior of individual bodies, thermodynamics deals with the average behavior of vast numbers of them. The central concept of statistical thermodynamics, as far as we are concerned in this chapter, is an expression derived by Ludwig Boltzmann, 1844 to 1906, towards the end of the 19th century. That was not long before he committed suicide, partly because he found intolerable the opposition to his ideas from colleagues who were not convinced about the reality of atoms. Just as the Zeroth law introduces the concept of temperature from the viewpoint of bulk properties, so the expression that Boltzmann derived introduces it from the viewpoint of atoms and illuminates its meaning. To understand the nature of Boltzmann's expression, we need to know that an atom can exist with only certain energies. This is the domain of quantum mechanics, but we do not need any of that subject's details, only that single conclusion. At a given temperature, in the bulk sense, a collection of atoms consist of some in their lowest energy state, their ground state, some in the next higher energy state, and so on, with populations that diminish in progressively higher energy states. When the populations of the states have settled down into their equilibrium populations, and although atoms continue to jump between energy levels, there is no net change in the populations. It turns out that these populations can be calculated from a knowledge of the energies of the states and a single parameter, the symbol for beta. Another way of thinking about the problem is to think of a series of shelves fixed at different heights on a wall, the shelves representing the allowed energy states and their heights the allowed energies. The nature of these energies is immaterial. They may correspond, for instance, to the translational, rotational, or vibrational motion of molecules. Then we think of tossing balls, representing the molecules at the shelves and noting where they land. It turns out that the most probable distribution of populations, the numbers of balls that land on each shelf, for a large number of throws, subject to the requirement that the total energy has a particular value, can be expressed in terms of that single parameter beta. The precise form of the distribution of the molecules over their allowed states, or the balls over the shelves, is called the Boltzmann distribution. This distribution is so important that it is important to see its form. To simplify matters, we shall express it in terms of the ratio of the population of a state of energy, E, to the population of the lowest state of energy, O. Population of state of energy E over population of state of energy O equals E to the power of minus beta E. We see that for states of progressively higher energy, the populations decrease exponentially. There are fewer balls on the high shelves than on the lower shelves. We also see that as the parameter beta increases, then the relative population of a state of given energy decreases and the balls sink down on the lower shelves. They retain their exponential distribution, with progressively fewer balls in the upper levels, but the populations die away more quickly with increasing energy. When the Boltzmann distribution is used to calculate the properties of a collection of molecules, such as the pressure of a gaseous sample, it turns out that it can be identified with the reciprocal of the absolute temperature. Specifically, beta equals 1 over kT, where K is a fundamental constant called Boltzmann's constant. To bring beta into line with the Kelvin temperature scale, K has the value 1.38 multiplied by 10 to the power minus 23 joules per Kelvin. Energy is reported in joules, J. 1 J equals 1 kilogram meters squared per second squared. We could think of 1 J as the energy of a 2 kilogram ball traveling at 1 meter per second. Each pulse of the human heart expends an energy of about 1 joule. The point to remember is that because beta is proportional to 1 over T, as the temperature goes up, beta goes down, and vice versa. There are several points worth making here. First, the huge importance of the Boltzmann distribution is that it reveals the molecular significance of temperature. Temperature is the parameter that tells us the most probable distribution of populations of molecules over the available states of a system at equilibrium. When the temperature is high, beta low, many states have significant populations. When the temperature is low, beta high, only the states close to the lowest state have significant populations. Regardless of the actual values of the populations, they invariably follow an exponential distribution of the kind given by the Boltzmann expression. In terms of our balls on shelves analogy, low temperatures, high beta, corresponds to our throwing the balls weakly at the shelves so that only the lowest are occupied. High temperatures, low beta, corresponds to our throwing the balls vigorously at the shelves, so that even high shelves are populated significantly. Temperature, then, is just a parameter that summarizes the relative populations of energy levels in a system at equilibrium. The second point is that beta is a more natural parameter for expressing temperature than T itself. Thus, whereas later we shall see that absolute zero of temperature, T equals 0, is unattainable in a finite number of steps, which may be puzzling, it is far less surprising that an infinite value of beta, the value of beta when T equals 0, is unattainable in a finite number of steps. However, although beta is the more natural way of expressing temperatures, it is ill-suited to everyday use. Thus, water freezes at 0 degrees Celsius, 273 kelvins, corresponding to beta equals 2.65 multiplied by 10 to the power 20 per joule, and boils at 100 degrees Celsius, 373 kelvins, corresponding to beta equals 1.94 multiplied by 10 to the power of 20 per joule. These are not values that spring readily off the tongue, nor are the values of beta that typify a cool day, 10 degrees Celsius corresponding to 2.56 multiplied by 10 to the power of 20 per joule, and a warmer one, 20 degrees Celsius, corresponding to 2.47 multiplied by 10 to the power of 20 per joule. The third point is that the existence and value of the fundamental constant K is simply a consequence of our insisting on using a conventional scale of temperature rather than the truly fundamental scale based on beta. The Fahrenheit, Celsius, and Kelvin scales are misguided. The reciprocal of temperature, essentially beta, is more meaningful, more natural as a measure of temperature. There is no hope, though, that it will ever be accepted, for history and the potency of simple numbers like 0 and 100, and even 32 and 212, are too deeply embedded in our culture, and just too convenient for everyday use. Although Boltzmann's constant K is commonly listed as a fundamental constant, it is actually only a recovery from a historical mistake. If Ludwig Boltzmann had done his work before Fahrenheit and Celsius had done theirs, then it would have been seen that beta was the natural measure of temperature and we might have become used to expressing temperatures in the units of inverse joules, with warmer systems at low values of beta and cooler systems at high values. However, conventions had become established with warmer systems at higher temperatures than cooler systems, and K was introduced. Through K beta equals 1 over T.
Sample complete. Ready to continue?